Okay, cool. Yeah, so I'm super excited to present this stuff. I've been working on looking at more of the basin correlation for the last year and a bit, and this is my first time presenting it, so I'm super excited. I'm not even going to bother covering this because Jared did a really good intro of why the Neoproterozoic is so important, and I think everyone here knows that. And as Alan said, I'm really just focusing on that transition into the Cryogenian, which is where we have the first of the Cryogenian glaciations, which is the Sturtian. So these Sturtian glacial deposits are fantastic because they are recorded on almost every continent. So from that figure in the bottom, you can see all the yellow and red dots are locations where we have found the Sturtian glacials. So they're very, very widespread. And in recent years, there has been a lot of analyses from these other notable sections. So some of them that I've highlighted is Scotland, Namibia, Ethiopia, Svalbard, and China, just to name a few of some of the research that has been done on the Sturtian glacials. And South Australia has some of the most well-exposed, continuous and thick sections of the Tonian to Cryogenian transition. So this project is really looking at the sedimentology and the geochemistry through this section over 8,000 meters in vertical stratigraphic thickness. So there hasn't been a lot of recent research on the Tonian strata in South Australia in particular. So this study is really good for filling in that gap of more contemporary work and also quite detailed insights into the Tonian depositional environment. There has been quite a lot of work done in the Cryogenian, especially Ashley. She's done fantastic work in the Cryogenian. And a lot of those are focused on specific formations. So this might help piece together some of the more stratigraphic changes through palaeoenvironment and also looking at the variation across the basin because we've highlighted a few sections across the northern Flinders. On the flip side of that, you have some fantastic work by Wolfgang, which really encompasses the Neoproterozoic as a whole across the basin, but you can sometimes lack the resolution. So because we've measured at meter scale, we've got quite detailed logs through the Tonian to Cryogenian. Again, I'm probably not going to go into this because it has been highlighted already what the Adelaide Rift Complex is. My work, you can see, is focused throughout the northern Flinders Ranges across to west to east transect. I'm just going to go over some of the language I'm going to be using in the presentation, just so you know where I'm talking about. So the first is the western margin, and that's encompassing 3 of my sections that I'll talk about in a second. The next is the north central zone, which has 1 section. We then have the Yanktonina anticline, where I've got a section from both of the limbs. And then in the Archit syncline in the east, I've just got one on the northern limb. And these sections vary quite a bit in thickness, just based on timing and exposure and things like that. On the western margin, our termination hill section was about 500 meters, and as was the North Copley section. My South Copley section was the thickest, and it has been used as a case study throughout a lot of my PhD, so it is the most detailed of all my sections. The North Central zone is funny. Jared and I actually struggled to even find the glaciers when we went there. It's incredibly thin. So we measured only a 150 meter section. Yanktonina anticline somewhere in the middle. You'll see the North Yanktonina section is very small. Jared and I were just passing through, so we just got that transition. And then in Archit, we did some more extensive logging. We got a 1,500 meter section. So this is a very broad overview of the sedimentology that we have collected in my project. As I said, it's an over 8,000 meters of total measured section at roughly 1 meter resolution. That did vary based on exposure and quality of outcrop and things like that. From this, we've got about 18 lithofacies, 6 facies associations, and 11 different depositional sub-environments. And they do represent multiple regressive transgressive cycles that I'll talk about a little bit later. And overall, these sort of represent 2 key settings, a carbonate platform and a glacier-marine setting. And within that, there's 3 key facies associations, which I'm going to go through with some pictures because we all like pretty rocks. So this is the first. This is the inner platform. These are some examples of some of the lithofacies we see in this facies association. Along the western margin, there's prevalent carbonate deposition. So this is in Copley and Termination Hill. And it's distinguished by TP structures and magnesite mineralogy. So there's obviously quite a lot of peritidal conditions, a lot of exposure, and also a lot of manganese-rich water. In the north central zone, so in Mount Lyndhurst and in Yanktonina, we see more balanced clastic carbonate deposition with a lot of laminated silts and layered microbialites. Oh, I should also just point out what you're looking at. So the TP structures are in photo D in the bottom left. Some of the magnesites are in E. And then in Archit, it had some beautiful sedimentology. It was very clastic dominated. and we had some heterolithic strata. So there's obviously a bit of tidal work at play, and that's where you can see those nice heterolithic strata in photo C, and also some mud cracks and ripples and things like that. So very dynamic environment. Moving into the outer platform, it tends to be stratigraphically associated with the inner platform and makes up part of the pre-glacial successions. And in the Copley and Mount Lyndhurst zones, this is where we see some microbial buildup. So they're very beautiful. You can see them in the bottom few figures. We've got columnar and conical stromatolites. And that's associated with these topographic highs, which I will talk about in a second, and relates back to what Rochelle was talking about in her presentation. And in Termination Hill and towards the east in Yankonina and Arkaroola, we see just very fine-grained carbonates and clastics, which you can see from figure A. So not all that exciting. And then we get into our slope to basin, and that really marks the post-glacial deposition across the basin. So on the western margin, we see some cross-stratification and fine-grained clastic and carbonate material, and that's like photo in B. In Yankonina, we see much more carbonate deposition. So this is a great place to try and get an understanding of those cap carbonates. Darwin actually has some of them at the minute, and he's going to do some analysis on them. And then in Arkaroola, we see some really cool slope deposits. So we have soft sediment deformation, which you can see in that big middle image, and also some breccia beds, and that sort of forms from these really steep slopes. Moving into the glacial environment, this is our ice margin Facies association, and this is commonly where we see the deposition of those big diamictites. In the north central zone, so that's in Mount Lyndhurst, it is very, very thin. As I said, Jared and I could barely find it. It's about 5 meters thick. And then when you go over to the east towards Arkaroola, it's incredibly thick. I'm sure a lot of you have been to Tillite Gorge. There is a lot of diamictite out there. And the section we measured was up to 1,000 meters. So very, very variable across the basin. We then get into the Ice-Proximal zone. This is where we start to see some flow dynamics. So it is comparably a lot thinner than the diamictite beds and more fine-grained. In the western margin and in Arkaroola, so along the edges of the basin, we see some evidence for cross-stratification. So there's obviously some sort of unidirectional currents at play. And then in Yankonina anticline, we see some orthoconglomerates and diamictite beds with scour and fill structures. So again, we've got some evidence for flow dynamics and possible channelization. These are probably the prettiest photos. This is our Ice-Distal. I just like pretty photos. So this is our Ice-Distal, and this really marks the top of the syn-glacial deposition. So when we're starting to move into the deglacial package. And this is where we see prevalent drop stones bearing down into really fine silts and things like that. So along the western margin, we have evidence for soft sediment deformation, which is the gorgeous load cast and flame structures. We also see ripples and ripple cross stratification, where you can see in that middle image some climbing ripples. Over in the north central and Arkaroola, I said it's not deposited. In the north central zone in Mount Lyndhurst, it wasn't. The glacial package was very thin. In Arkaroola, we had some gaps in stratigraphy, so it very well could be there, just where we measured, we didn't see it. All right, so getting through all of that, we then wanted to piece it together and try and see how they all fit in, because they're obviously spread over 150 kilometers. Do they connect, and how do they connect? So we sort of came up with this fence diagram, if you will, of our different Facies associations. And we based this off the lithostratigraphy. So what were the different lithologies and what were the stacking patterns? So how were they related genetically into time intervals? And then from that, we started to think about the sequence stratigraphy, which is sort of what Rochelle was talking about a bit before. So the interaction between accommodation space and sediment input, and that's controlled by, was it the, I don't know which one you said, Rochelle, was it allo? You know the one I'm talking about, the big scale stuff. So tectonics, Ice-Distal climate and things like that. So this is our sequence stratigraphic correlation across the northern Flinders Ranges. And I'm just going to go through and break it up into the pre-glacial, syn-glacial and post-glacial. So in the pre-glacial, along the western margin, we have a very shallow platform geometry, and that makes it very, very sensitive to flooding events. So you'll notice along from Termination Hill to South Copley, we have quite a few of these dark grey areas, which are our transgressive systems tracks. So where relative sea level is rising. And that's likely just because of the shape of the platform. It's very shallow, very sensitive to flooding events. When we move into the north central zone, so in Mount Lyndhurst, we have this topographic high. Now, this is likely to do with some salt diaprism. I said I'd get back to what Rochelle was talking about. There is a large salt diapir near Mount Lyndhurst. I think it's called the Mount Lyndhurst diapir. And this is likely creating this really shallow or really high platform, which is, what am I trying to say? Oh yes, which creates a wonderful environment for these stromatolites to grow. Nice, shallow, warm water. That's why we tend to find these big microbial buildups in this area. Then we get over to the Yankonida anticline, which is in here. And it's just got a lot of fine-grained material, likely due to a more distal setting as well. In Arkaroola, we have a lot of plastic material, which I mentioned earlier. That's likely to do, again, with its relatively close proximity to local faulting and source material. So we're just sourcing a lot of plastic material. There's a lot of faulting going on in that eastern margin. Then moving into the glacials. So along the western margin, again, we have this platform geometry. And because of this, we tend to find diamictites that appear to be very close to the glacier themselves. So ice contact till. In the north central zone, so over in Mount Lyndhurst, we have very thin deposition. As I mentioned, that's probably to do with just the topographic high. In Yankonida, we have more paleo valleys, so there's more space to fill, and that's why we have slightly thicker deposition of the glacials. And then in Arkaroola, we have quite a lot of glacial erosion and continued faulting through the Sturtian, which has created space for all this material to go into the post-glacial. In most areas, we see this widespread transgression where we move into a more subtidal area and we're depositing a lot of fine-grained plastics and carbonates. The only one that looks slightly different is Arkaroola, which is where we see those slope deposits. So that's likely to do with really steep escarpments and depositing material as slope debris. Cool, so you can't really see, but yes, what I wanted to do was just think about how this all fits into the global context. Obviously understanding our basin is super important, but trying to see how it fits in to the wider scheme of things can be quite useful. And I wanted to just pick out a few key sites and a few key basins in other areas to see how they compare to our section. So as you can see, I've highlighted South China, Northern Ethiopia, Namibia, Western United States, Northern Canada, Svalbard and Scotland, just as a few examples. So in general, for the pre-glacial package, they tend to deposit very similar material to South Australia. So a mix of plastic and carbonates in more or less a marginal marine to subtidal setting. In the Western United States, Canada and South China and Namibia, they also have active rifting occurring during this time. So a lot of this is largely rift related. So tectonism played a large part in these particular locations. Scotland and Svalbard were slightly different. So you can see they're located over here and they were going through a period of thermal subsidence at the time. So they were in a slightly different tectonic regime. And Northern Ethiopia, again, was quite different. That was experiencing rollback in a back arc setting. So that's over here. And that was followed by a period of thermal subsidence. The syn-glacials, in terms of their lithologies, are quite similar. So they have diamictite packages separated by finer grain units, just as we do in South Australia. And overall, they represent a glacier marine setting. So again, the Western United States and Northern Canada is very comparable to our section in South Australia. They do record 2 glacial advanced retreat cycles and did have active faulting and rifting at the time, just like in South Australia. South China and Namibia are a little bit contentious. There has been argued that there was 2 glacial advanced retreat cycles, but there has also been the flip side of the argument that there was one long sustained glaciation. In Scotland, it's got several glacial cycles. It's quite a thick succession, and they've recorded much more than 2. In Svalbard, it's a very, very thin unit. They've only got that one diamictite package. I guess similar to my Mount Lyndhurst section. It's very thin. And then in Northern Ethiopia, they continue to have deposition in the subsiding tectonic setting. Once we get to the post-glacial succession, again, the facies are very similar across the globe. We see an abundance of fine plastic and carbonate material, and overall in a more subtidal to basinal setting. So in Western USA, Northern Canada and South China, they do show evidence for a transgression, and as we'd expect, that's likely driven by the melting of large glaciers that have increased relative sea level. And they also have transitioned to a phase of subsidence. So that's similar to what we see in South Australia. In Svalbard, they do record a transition to a deeper setting, but that doesn't seem to be to do with any sort of change in their rift or their tectonic regimes. In Namibia and Scotland, they do have shallow water deposition relative to the other locations I looked at, and that's likely because they're going through quite different tectonic regimes at the time. Namibia was in a phase of active uplift, and Scotland was in a phase of slow subsidence, so it allowed for a smaller accommodation space and a more shallower setting. All right, I'm getting towards the end. I have no idea how long I've been going for. So this is some of the work I have been doing recently for my last paper, and this is now sort of looking at the geochemical correlation across the basin. So my first paper was very much focused on the sedimentary what am I trying to say? Sedimentology, thank you. Sedimentology and sequence stratigraphy. And then this is sort of looking at more at the isotopic correlation. So I know this is quite a busy figure, so I'll just talk about what I've got here. I've got all my sections. These plots represent the delta 13C along the bottom axis. And the color of the dots is the cerium anomaly. So I wanted to look at the relationship between isotopes and trace elements to see if we could build a better picture of what the water column was like at the time. So cerium has been used as a proxy for redox conditions. So when you have a more negative cerium anomaly, you have more oxic conditions. And when you are in more of an anoxic setting, you have a higher cerium anomaly. I also looked at europium. So that, where's my mouse? That's represented by the size of the dots. So the larger the dot, the larger the europium anomaly. Europium can show you a few different things. It's been used as a proxy for redox as well. It also has been used to understand whether you're close to a hydrothermal source. So if you have an increased europium, you could be close to a hydrothermal source. But also on the flip side of that, you can also get increased europium from having a large input of feldspars. So that could be from continental weathering. So it's not that easy to look at it in isolation. You have to sort of look at it with a bunch of other evidence. So what I've got here is an opportunity to see whether the fluctuations in delta 13C can be correlated across the basin. I do have several negative excursions I'm going to talk through. So starting in the Skilly, we have a negative excursion in the Termination Hill section by 10 per mil, which is quite a lot, and in South Cockley by 5.5. In terms of the cerium, you can see by the color, it's slightly negative. So it's around 0.8, not significant, but it is slightly negative. And the europium is negligible. It's quite low, it's around 1. These tend to be associated with packages of peritidal magnesites. And they also, interestingly, coincide with minor regressive surfaces. So that goes back to my sequence stratigraphy. Minor regressive surfaces just show relative drops in sea level. So what we think might be happening here is because we've got a relative drop in sea level, we have an increase of riverine input. River water is isotopically light in carbon, so it will reduce our delta 13C. And then once we increase the carbon burial, it recovers quite quickly because delta 13C becomes becomes heavier when we start to bury organic carbon. So you'll notice that these excursions are quite rapid and they recover quite quickly. So they come out and then recover quite quickly. So that is the only excursion we found in the Skilly. There's quite a few in the Myrtle Springs. So we have this first one in the base of the Myrtle Springs, just here. And that's in the South Copley section, and it's by 8 per mil. You'll notice the cerium is a little bit larger in this one. So it's a lot closer to 1 based on the color. So it's more up here. So it's negligible. And that probably means that it's less oxic. It's more of an anoxic signature. Again, europium negligible. Just as a little disclaimer, europium doesn't show much for any of these. So I might as well just stop talking about it. These tend to be associated with more distal subtidal silts. and they coincide with the maximum flooding surface. So water level is actually rising. And that sort of fits what we understand for the stratification of the oceans at the time. We did have more anoxic deep waters and oxic shallow waters. So if we do have this deepening event, we're likely to have moved into a more anoxic deep water setting, which would drive our cerium anomaly up, and it would make the environment less productive. And so that might have facilitated this negative excursion. Moving up through the Metal Springs Formation, we see another negative excursion, and that's found at two locations, in South Copley and also in South Yanconina. In South Copley, it's by 4.5, South Yanconina by 3.2, so quite similar. This is associated with platformal carbonates, which are interbedded with quite a bit of clastic material. This coincides with the high stand systems tracks. That's again a shallowing event where we have the continental material building out into the ocean. So we think it's quite similar to the first excursion we saw in the Skillygalee, where we have an input from isotopically light riverine water. It drives the delta 13C down. Moving up again, South Yanconina, we have another excursion. This one's quite a bit more significant. It's about in the middle of the formation by 7.5 per mil, and it's associated with subtidal dolomites. So we've gone deeper again. This coincides with a transgressive event, so a deepening event. So we think it's quite similar to the one in the base of the Myrtle Springs, where we have a less productive anoxic setting, which drives the delta 13C down. And the last one we see is in the top of the North Yanconina section here, negative excursion by 6 per mil, so it's again quite significant. It's associated with inner platform carbonates. So again, we're going through a shallowing event, a high stand systems track. The continental material is building out into the ocean. So again, we think we might be seeing increased input from isotopically light riverine carbon. So there's obviously a couple of different things at play here, and I really wanted to try and understand whether there is a relationship between the geochemistry, the sedimentology, and the sequence stratigraphy. My next step is trying to see whether we can correlate those globally. So I did it with the sedimentology, and I was curious to see if we could do it geochemically. I have just plonked in a figure from a paper that is fabulous by Park et al. And he compiled an extraordinary number of data sets from all over the globe and tried to see if they could make a compilation of all the delta 13C data and whether there was overlaps with the anomalies we see worldwide. This is what I'm currently doing. I don't actually have my data to overlay. It's what I'm working on now. So when I do have it, if you're curious, just hit me up and I'll let you know what we come up with. But we're hoping to see some overlap. So some of the negative excursions that we see in the Skillygalee and the Myrtle Springs, we're hoping to see mirrored in the global section. Thank you.